Hi, everybody. All right, we are starting into chapter 3, and this is the last 3 sections that we'll do before your first test. So we're delving deeper into differentiation and derivatives. Um, in 3.1, the major highlights are gonna be looking at some alternative notation for derivatives and just starting to get used to that. And then also looking at the idea of differentiability. So very similar to the idea of continuity, but now we're asking ourselves the question, when do derivatives actually exist and do they exist at this certain point kind of a thing. In 3.2, we're going to start looking at things like the power rule, the product rule, the quotient rule. Um, So those things that for you who have taken calculus before, those are coming in. We're not going to have to rely on the limit definition of the derivative for too much longer. It's important as as a conceptual kind of construct, but practically we're going to be able to have a library of familiar functions that we're able to memorize what their derivatives are and how we have certain rules to combine various functions. So the practical calculation of derivatives is going to be easier than taking big long limits. Um, and then in 3.3, we're going to look at the derivatives of some trigonometric functions. And I am also strategically bringing the exponential functions down into 3.3. It just makes more sense to me down there. So we're doing 3.1 and 3.2 right now. Let's get into it. Okay. Um, First is some notation and considering some notation for higher derivatives as well. So the derivative, slope function. Um, the two most things that look most slopey are this dy dx and this df dx. Both of those are alternative ways of saying the exact same thing. Very often in calculus, we'll define, our output variable y as a function of x. And so saying dy dx or df dx is really just talking about the rise over run of this function. Now, these if we pick it apart and we look at df and dx as their own things, we call the little things differentials. Differential. And we've started talking about those as tiny nudges. When it says df, it means a tiny nudge to the function's output, f. And when we say dx, we mean a tiny nudge to the input, x. Um, in calculus in modern times, these differentials are defined using the derivative. And that's going to happen later on in chapter 3. So these things don't really have their own definition yet. They're defined in terms of the derivative. We'll see that later. For right now, think of them as tiny nudges. Like back in Newton and Leibniz's day, these differentials were infinitesimals, meaning that they were like super, super, super small numbers. Like think 1 over infinity as being a super, super, super small number. It's weird to think about, but that's what we're doing. And, all of this happens because fundamentally, I guess it would be good to look at the limit definition real quick. Um, Limit definition as, let's go, h goes to 0. Um, we've got a difference of y values on top of this fraction, and then h is its own difference of x values. Um, and so where was I going with this differential? The idea is, yeah, when we let h go to 0, It's very similar to the idea of a fraction getting smaller and smaller and smaller and approaching zero the larger that you make the denominator of that fraction. So right now, I know that this is not defined super strategically or super rigorously, but we will look at differentials. They're defined in terms of the derivative in a later section. Anyways, dy dx and df dx are both there. Think rise over run. Think tiny nudges in the rise and tiny nudges in the run. That's the main thing that we want you to focus on for right now. Okay. Also, we will definitely be using this f prime notation. That's one that we're going to use to denote the first derivative. Um, this y prime is something that we will utilize a little bit more in Calc 2, and you'll use it in differential equations. Um, it's just a different notation that gets utilized more often then. Um, this notation with d over dx out in front of f of x, that means the exact same thing. Here, d over dx is acting more like a derivative, oh geez, derivative operator, kind of saying take the derivative of f with respect to x. This one feels just like a little bit more bossy, like it's telling you to do something. Um, but all of these are legitimately the same thing. The ones with the big D's, those, we don't use in calculus very much. You might see them, in different books later on in your mathematical lives, but we don't really use this notation very much. Um, Moving on to second derivatives and higher order derivatives. Generally, we continue to use the prime notation. We just do a double prime thing whenever we're trying to get the second derivative of x, which just means it's the derivative of the derivative. Um, and we tend to use the the prime, the little apostrophes up there, that prime notation. We would go up to f triple prime, but we normally, if we're going to f the fourth derivative, um, normally we would write that as a 4 in parentheses, like this notation is saying. So the nth derivative, we normally write it that way because there gets to be too many little lines in a row, too many tally marks. Um, so yeah, those will definitely be used. Gosh, this notation, I can imagine it being confusing. Here and here, what is going on? Those, squareds are maybe in a different spot than you would expect. I think probably the way that this new notation makes the most sense is taking cues from this one that I called a derivative operator. So imagine what would happen if we threw in another d over dx telling us take the derivative of, f with respect to x again. It would mean that we stack two of these, right in front of each other. So d over dx, d over dx of f of x. And so what ends up happening is this d over dx thing appears twice, and that's why we write the d squared over dx squared part out in front, and f doesn't have a squared part on it. It's because f is really kind of the object of this derivative operator happening twice. I know it's strange notation, but that's the way it is. And I guess, these boxes next to it kind of reinforce that, yeah, that's what we're doing. We're utilizing that derivative operator again. So maybe those purple boxes help you connect to that pink boxes. And then, yeah, all the rest of these big Ds, not paying attention to those. But yeah, in general, when we go up to higher derivatives, the nth derivative, the numbers go here. Anyways, let's keep going. Example 3, I'm skipping a couple here. This part of the text has more examples of using the limit definition of the derivative. And like, if we wanted to practice that more, we could, but we already got some extra practice using the activity. If you want to practice using the limit definition of the derivative more with me, that would totally be fine. But I don't know. Maybe I'm of the opinion that a little bit of the limit definition goes a long way, and we don't have to, you know, destroy ourselves doing that. So even though the text uses the limit definition on this one, we've already done the limit definition on quadratics so much. Oh, wait. No, this is exactly where I wanted to be. This is coming from, last week or, a couple sessions ago. This is section 2.6. Okay, yeah, 2.6. Here we use the limit definition on a quadratic, and we did all that good stuff. So I don't feel like we need to do limit definition on a quadratic again. What we're going to do is we are going to use the power rule. Just to remind you, we talked about the power rule a little bit here on, Wednesday. It's if you take the derivative of x to the n, what you end up getting out is whatever was in that exponent times x to the n minus 1 in the exponent. So it feels like you're bringing down the exponent and multiplying the exponent and then subtracting 1 from the exponent. But this is a pattern that, we could prove that this pattern exists if we did the limit definition of the derivative out. But yeah, this is just a pattern that continues to happen with polynomials. So we're going to utilize this with this function. And the main thing that I want to focus on is just the fact that position, velocity, acceleration, and jerk are all rates of change of each other. They're all related, which is a cool thing. So I'm going to open up GeoGebra real quick and just get an idea for this. Here we're looking at some projectile motion. So, imagine that this is a height and this dimension is time, really. So this is happening over time. But imagine somebody throwing like a rock up into the air and, the rock continues to get higher and higher and higher, but it slows down how fast it's going up and then it starts going down because gravity is a thing. So gravity is a force that is constantly pulling on this and slowing, the rate of change that started off in a positive direction, and it, continues to add up and brings it back down. So acceleration on Earth's surface, we treat it like it's a constant. That constant, when we're looking at feet per second, is negative 32, just saying that it's pointed in a downwards direction. So if we were looking at acceleration as a function, it is a completely constant flat function with a derivative of 0. It's completely horizontal. Velocity is the antiderivative of acceleration, but it's the derivative of the height function. And so, yeah, you can see the power rule happening here. the position function is a quadratic, the velocity function is a line, the acceleration function is a constant, -32. Let's go back and just write this out here. Um, just making use of the derivative notation as well. Okay, so h of t is -16 t squared plus 96t plus 4. Cool. I guess, it doesn't hurt to know. This is another little aside, but uh, 96, this number is actually going to work out to be the initial velocity. So this thing is being velocity. Um, it's being thrown at 96 feet per second upward. And this 4 is the initial position. It means that the ball is starting 4 feet off of the ground. So that's kind of cool that it shows up in this quadratic equation. Anyways, we're focused on derivatives. If I take the first derivative of h, I could write it like this. I could write it as dh dt. That would be another natural way to write it. But, when I do that, I'm going to utilize the power rule. And since I've got a 2 in the power on t, I'm going to bring that down and multiply it times 16, and that gives us a -32t. I'm also going to use the power rule on the 96t part. And since there's a 1 as a power on the t, I'm going to multiply 96 times 1 and get 96. Notice that the t goes away now because t has the power of 0 on it right now, which is just 1. And here, the power on t is dropped by 1 as well. So this is a good function for the derivative. I guess, I should say that this one is the velocity function. But yeah, the velocity is the first derivative of the position function. That's the one that turns out to be a line. If we do a second derivative, that would be d squared h over dt squared, according to that new notation that we're learning. Or equivalently, probably the more, familiar one is h double prime t, so we're saying second derivative. But we use the power rule again, we get -32, and the 96 turns into a 0. We're going to look at the constant rule, but for the 96 part, you're asking yourself, if I have a line that's completely horizontal at y equals 96, what's the slope of that line? The slope of that line is 0. So it does not show up in the second derivative. But yeah, that's the second derivative. That's the acceleration function. If we go to a third derivative, it would look like this. Oh, shoot. Forgot to write the h. There we go. dt squared or dt cubed. Yikes. There we go. It would be h triple prime. This one would just turn out to be plain old 0. And yeah, they mention jerk in this section, so I wanted to mention it in this problem. Jerk is the rate of change of acceleration. And the way that I would think of that is there some new force that is being added to the system that is changing the acceleration of the object? So it's the rate of change of acceleration. And in this case, when we're just flying through the air, the jerk we would consider equal to 0 because the acceleration due to gravity is not changing. There's not an additional rocket booster on this tennis ball that is adding a different kind of force to the situation and, changing the acceleration. So that's that. Pretty good. And we saw that, yeah, all of those decrease in a power because we're working with a polynomial function. So that's pretty cool. Um, Example 4 is just another way that we can look at all three, you know, first three derivatives of this function all on top of each other. Here, we're starting up a power bigger than the previous example. We're starting with a cubic function rather than a quadratic. But yeah, we've got this nice cubic as the parent function, f. And then we've got f prime, the first derivative, is a quadratic. F double prime is linear, and then F triple prime is a constant. And again, you can like, it's super cool that you can look at any pair of one of these functions and its derivative, and the slopes that you see on the original function are the y values that you see on the derivative. So I don't know, real quick, let's do this again. Maybe we do it with the cubic part of this. Goodness. All right, let's see. I'm gonna use what'll show up. We've got purple. All right, purple's a new color. Um, hmm. Let's think about the original function and let's find some interesting slopes there. So let's say here on the function f and here on the function f, we get some places where there are horizontal slopes. That means that when we look at the derivative, we're expecting that those are places where the y value is equal to 0. So at those same x values, we see that the y value is equal to 0. So flat slope on f means 0 y value on f prime. Um, and again, if we did the same thing for the red and the green functions, 0 slope on the red function leads to a 0 y value on the green one. And we could play this game, like we could do it for all of those. And I would definitely encourage you to do it until you see it. It's going to show up on an activity pretty soon. So anyways, there's a cool relationship between all of these. Let's keep going. The next major idea in this section is differentiability, and it's very related to continuity. We're asking, when are we able to take a derivative, and when will that exist? We look at this limit, the limit as h goes to 0 of f of c plus h minus f of c all over h. And we need to consider this limit happening from both sides. So we need to approach 0 from the right, and we need to approach 0 from the left when we're considering differentiability. It's like when we were looking at continuity with limits, we were interested in taking a limit from the right, a limit from the left, making sure that those matched, and then checking to see that that limiting value actually matched the function value. In differentiability, we're working with this limit that's based on the difference quotient, and we're asking ourselves, do the secant lines approach the same tangent line from both the left and the right? So let's take a look at some examples, and we'll try to decide when we are when we're differentiable and when we're not. So this first function is a nice smooth, it looks like a quadratic, um, a nice smooth curve where if we were making secant lines and getting the points that are determining the secant line closer and closer together, um, there's not a jagged change. Like if we approach from the right, we tend to approach this red line, the red tangent line. Um, if we came from the left, we would also approach that red tangent line. Maybe I could try to do a good job coming from the left because we've already got the right there. Let's use a green. So if I was out here and I was using this point to make a secant line, I could draw that line with the point of interest. I could scooch this a little bit closer and maybe get this one. And you can see that, yeah, the slope has changed. It's gotten a little bit flatter. But if we get a third point that's really, really close to the point of interest, and I make another line, the slope of this secant line, almost matches the tangent line, um, completely. So the idea here is that coming from the right or coming from the left, we still approach the same slope, which is what we're looking for when we're differentiable. In contrast, the absolute value function to the right here, if we were taking, any slope over here, we could, measure this slope as being a slope of -1. If we were coming from the right, we could measure this slope as a +1. And then the limit from the left and the limit from the right don't match when we come to this point at the end. We've got this hard, jagged point, um, where the limit of the slope of these tangent, or yeah, the limit of the slopes of these lines don't match up. So this point, at x equals 0, um, this function, absolute value of x, is not differentiable. And then I should just say at x equals 0. Everywhere else, we can come up with a slope for this absolute value function. But at that single point, we don't know exactly where to put it. It could be really anything. So it's not defined. The left-hand limit doesn't match the right-hand limit. Um, Same thing happens for the square root of the absolute value of x. Here, we're coming to what's called a cusp, where it looks from the right that the slope feels very, very positive as we go towards 0. And as we come in from the left, the slope gets very, very negative. This is a little bit more complex because, the slope's changing, whereas these slopes weren't changing, but it's the same kind of scenario where the limit from the left, very negative slope, doesn't match the limit from the right, a very positive slope. So this one, again, is not differentiable at x equals 0. Um, the cube root of x is kind of an interesting scenario where this function is nice and continuous, um, but if we follow the tangent lines as x approaches 0, um, these tangent lines look vertical. And so we wouldn't be able to put a finite number slope on this. We wouldn't say that we could, f prime of x is equal to, we can't say f prime of x, or sorry, f prime, let's say at 0 is a million, because it's not a million. It's actually a completely vertical slope. The closest thing that we could say is infinity, but even that, we don't really write that very often. Um, we could definitely say that it has a vertical tangent line there. Probably, the best thing to say is that f has vertical tangent line at x equals 0 for this scenario. So that's, it's special. It's technically a place where the derivative doesn't exist for the same reason that we were looking at, limits that go to infinity and stuff like that. Here we're not technically differentiable, but we do have a vertical tangent line. Um, okay. There is a relationship between differentiability and continuity, because if you're differentiable, you're guaranteed to be continuous, but it doesn't work the other way around. So one example of that would be this weird x times sine of 1 over x function. Um, that's what the subject of example 5 is. Here we're defining it in a piecewise function so that we can follow this for every value where x is not equal to 0, and we can leave a hole there. But then we can plug the hole in the middle using the second part of this so that when x is equal to 0, the y value is equal to 0. So we plug in the origin, and then we have a nice, well-defined continuous function. We showed that um, the limit of this function at x equals 0 would be 0. We used it using the squeeze theorem earlier on in class. Um, and so that blue wavy line, that blue wavy curve is continuous, but as you get closer and closer to x equals 0, the origin, um, that's going to continue waving up and down. And so the the y value will go to 0, but the slope is going to continue to change on and on and on, and that's never going to stop. Um, to show that it doesn't change, we could take a look at this difference quotient. So, we could actually go up and, do the limit definition of derivative on this thing. Um, Yeah. If we start throwing these in, this is the alternative way of looking at, the limit definition of the derivative. Normally, we would put an h on the bottom, but this is the one where technically this is the limit as x approaches 0. This is the formulation where we still have rise over run, but we're not talking about the gap between x values. We're talking about x being the slidable x value and 0 the one that's staying stationary. Um, so yeah, we're taking the limit as x equals 0 of all of this stuff. And you can see that, yeah, we get x over 1, x of, sorry, x times sine of 1 over x over x on the bottom. Those x's cancel, and we're still left with sine of 1 over x. Now, if you remember, this is the one with the oscillating discontinuity. Um, so from either side, this one doesn't shrink as it goes towards the origin. It just keeps waving. So this one is the one that waves really, 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 really fast, really, 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 really fast, and then it kind of tapers out. But we called this an oscillating discontinuity in the limit section, and it is, the way that we understand that the slopes of this function do not settle down and reach an actual value that we can call the derivative or the slope at that point. So this is another thing where we've got a continuous function, but we are not differentiable at that point. Cool. Let's keep going. Technically, there are these things called one-sided derivatives. It just means that you're looking at the limit from the right or the limit from the left. This could be important if you're looking at the endpoints of an interval that we're going to do very soon here. So, if you've got an interval like this and a is at the beginning, you might want to look at the right-hand derivative so that you can find the slope at the very first point in that interval. And same with the endpoint. That's going to be useful. I'm going to skip example 6 for right now. And I know that Darboux theorem is coming up. Darboux theorem is the intermediate value theorem, but it's the intermediate value theorem applied to derivatives. So the idea is if we have a nice, well-behaved differentiable function on a closed interval AB, then the derivative is going to take on every value between the right-hand derivative at the beginning point and the left-hand derivative at the end point, So basically, the first slope that you would get in the interval versus the last slope that you would get in the interval, maybe those things are different. If one of them is positive and the other one's negative, what Darbo's theorem is saying is that as this function goes between, maybe a negative derivative to a positive derivative, it's going to reach every single different slope in between the starting and ending slopes that you see. So it has that intermediate value property that, like, for instance, if you had a negative slope at the beginning and a positive slope at the end, you are guaranteed somewhere in that interval to have a slope of 0 if you are a differentiable function. Um, and I guess I made this for Darbo's theorem, which was complicated and probably more trouble than it was worth. But the idea here is that maybe we're looking at this function where we're starting off at our interval at -1 and our ending of our x interval is at 3. And at the beginning of the interval, we have a slope of -1. And at the end of the interval, we have a slope of, well, I guess, what's the slope here of h? The slope would be 3 squared minus 2. So it would be 9 minus 2. Okay, it looks like the slope is 7. I guess that makes sense. So we're going from -1 up to a slope of 7. The idea is every slope between -1 and 7 should be found somewhere along this curve. And actually, the way that I, did this was kind of silly, but I tried to do it so that I could reverse engineer things to be able to say, if I want to find a slope of -1, where would I find it on this line? And so, you know, I did that, reversed engineered things to make it happen. If I specify that I want to find a slope of 0, that's what I did, and it goes all the way up. So this was mainly just to show you that yes, indeed, along this curve, we definitely achieve all of the slopes in between -1 and 7, the slopes at the different endpoints. And notice that in order to get all of those slopes, I didn't even have to use this part of the function. This part of the function is actually kind of steeper in a negative direction than the very beginning. And that's okay. All this says is that we get all of the different slopes between -1 and 7 along, something like that. Okay, so we skipped to Darbo's theorem there. Um, to show you a case where we need to look at the right-hand derivative and left-hand derivative. It's totally cool. Let's go take a quick look at example 6. Here we've got a piecewise function, and the idea is, not only do we want to stitch this piecewise function together so that the two parts of the piecewise function hit the same y value, but wouldn't it be awesome if we could make two parts of a piecewise value or a piecewise function that actually meet up at the same slope, the same derivative, at the point where they're stitched together? It would mean that we could have a differentiable function that's defined in a piecewise manner, which would be super cool. So what we're going to do is use one-sided derivatives to make sure that the different slopes coming from the left and coming from the right actually match up. And so coming from the left, we would be using the square root function. Um, that's leading up to 1 coming from the left. So we would do this kind of, a, a limit to find out that the slope as x approaches 1 will be 2. So that's cool. Oh, actually, hold up. Just kidding. This limit is just for the y value. My bad. This limit's just for the y value. It makes sure that we match up with the y values and that we're actually continuous. What we want to do is look at these difference quotients. This one is the one coming from the left. This one's the one coming from the right. And so we're utilizing that square root function here coming from the left. We're using this quadratic function coming from the right. And the cool thing is that when you work these out, both of those limit definition of the derivative things work out to be the same slope of 1. So in the end, we get to stitch these together, and they both have a slope of 1, meaning that the function f is differentiable on this entire interval, which is pretty cool. All right, so we already talked about Darbo's theorem, and we're getting into 3.2. 3.2, we're going to look at just a bunch of little rules here, and the most interesting new things that we'll look here at the end of class are probably the product rule. The constant rule says that if you've got a function that is just constant at, just one y value, it means that the slope is equal to 0. Horizontal line, slope is equal to 0. So the derivative of any constant just goes to 0. Here's the positive integer power rule that we've talked about a couple times now. So that is a thing. The constant multiple rule, if you multiply, a function times some constant number k, it's completely fine to pull that k outside of the derivative and just let it come along for the ride. It really just means that, we looked at what does k times f of x happen early on in chapter 1. It's a vertical stretch. And when that vertical stretch happens to the function, it stretches all the, the slopes as well, but it stretches all of those slopes by the same scale factor. So, pulling that out to the front has the same exact effect. No big deal. Constant multiple rule works out nicely. Sum and difference rules, there's going to be a cool illustration of this on the video that you're going to watch from 3 Blue 1 Brown. This just means that the derivative of a sum of two functions is the sum of the derivative of those two functions. So basically, you can take those derivatives independently and add them up. It means that, yeah, finding the slope of the sum of a function, of the sum of two functions is that sum. And same with the difference. Those things work out really nicely. If you ever hear that the derivative operator is linear, it means that this property holds and this property holds. That's something that maybe we'll discuss a little bit more when we get to linear algebra, not this coming spring, but the next one after that for many of you. Cool. So example 2, if you want to pause and try these on your own, you're totally welcome to. I'm going to try to just go through them quickly, but feel free to pause if you have any questions or anything like that. Here we're just using, all right, so part A, we've got a nice little polynomial there. If we use the positive integer power rule there, we're bringing that 2 down so that this becomes 4x, and we're leaving just a power of 1 on the x because that 2 gets subtracted by 1. So that first term becomes 4x, and then the second term becomes 3. Both of those are positive integer power rules. It happens twice. Technically, we can do the positive integer power rule twice because the sum rule is a thing. So technically, we're using the sum rule and the power rule on the same problem. For part B, we get 3x squared. We get 3x because that 2 cancels out with the, half on the bottom. We get a -5, and the 7 on the end goes to 0 in the derivative. That part wouldn't have any slope. Um, cool. So wait a second. This is q prime. I didn't write that at all. So that's q prime of x. And then for part C, um, how can we use the power rule on this part? Well, um, let's go ahead and rewrite f of x first. Um, if we write this as 3 times x to the 1/2, then we see that coming in, to play. So if we write these roots or, this division by x as a negative exponent, oh geez. So if we write 1 over x as x to the negative 1, um, now those numbers are in the exponent, and we can apply the integer power rule here so that f prime of x would become, well, we're bringing down that 1/2 so that we get 3 halves out in front, and then we're subtracting 1 from the power, so this actually becomes negative 1/2 in the power. On the second part, we're bringing down that negative 1, so the minus sign that we have turns into a plus sign. We still have the 2 hanging out, and then we subtract 1 from the power so that that becomes negative 2. And if we wanted to rewrite this in terms of square roots and such, we could say that this is 3 over 2 square root of x. So just rewriting x to the negative 1/2 like that. And then we could rewrite this as 2 over x squared if we wanted to write it that way. Yeah, all that's good. So just that's some practice with power functions. Cool. This is where the book introduces e to the x. E to the x has this really cool property that it's its own derivative, um, which is great. And we're going to look at that, but we're going to look at it along with the trig functions towards the end. I'm not going to do it today. The main thing is that normally in class, we would watch the visualizing product and chain rules on YouTube. If I open up, oh my goodness, there we go. This one. It's this video from 3 Blue 1 Brown. It should be on our YouTube playlist. It's about 15 minutes long. So you can, like, after I'm done talking here, you can go ahead and start watching this. I don't think it makes sense for me to like record this on Zoom. So go ahead and just watch this on YouTube after this video is done, for the remainder of class. If you finish it, great. If you don't finish it, no worries. We can pick up from wherever. The most important parts to look at, probably the sum rule part is nice to see. It's a good visualization. And then the product rule part is also really cool. We can save the chain rule for later. That's not super important because we don't get to chain rule until like 3-4, 3-5. That won't even be on the first test, so not a huge deal. Anyways, I think before the video, maybe if I just real quick talk to you about what the product rule is using a picture from our book, maybe that would be good. The video will probably do a better job anyway. All right. Anyways, we looked at the sum rule, and the sum rule was, oh, hey, we add these two functions together and then take the derivative. It's the same as taking the derivative of the first function and adding it to the derivative of the second. That one works really nice. But the product rule is not just as simply, taking the derivative of the product of two functions is not the derivative of the first one times the derivative of the second one. It's more complicated than that. Same thing with a quotient. It does not work this nicely. It's more complicated than this. And so the picture that we want to have in our head when we're thinking about the product rule is a rectangle. And we saw rectangles like this on the activity. So it's not completely foreign, although I understand that that was a pain point. We can do this. What are we looking at with this rectangle? Well, we are trying to look at the product of f of x times g of x. So if I go purple here, and I just wanted to look at f of x times g of x, well, that is the area of this rectangle because, you know, this side is of length g of x, and this length is of side f of x. And they've shortened g of x into v, they've shortened f of x into u for purposes of just visualizing this. But yeah, the area of that rectangle is the product f of x times g of x. And when we're doing the product rule, we're taking the derivative of this product, meaning we're asking how fast is this area changing when I give it a little nudge? So uh, what happens is when we give x a little nudge, um, x produces a nudge in the function f. And so what they've labeled as delta u here, I would label this as like a df in the notation that we've been working with before. This one is, this is f of x, but this part over here is a nudge to the f function. And similarly, this side is, g of x, but this little segment where they're calling delta v, I would like to call it dg. Oh, geez. dg. Um, and remember from those other ones, the real change that is happening here can be captured by the two rectangles that are long and skinny. Um, these ones are the important ones for the product rule. And so the one on the top, if we look at the dimensions of this rectangle, we've got f of x as one of the dimensions, and then we've got dg as the other dimension on this green rectangle. And so what we end up getting is f of x for the base, and then dg for the height, but we're recognizing that we're trying to calculate what happens as we're trying to capture the rate of change of this rectangle. And so a dx belongs here as well. Trust me on that for right now. Hopefully you'll see it again in the video and it'll make sense. For the blue rectangle, one of the dimensions is g of x, and the other dimension is df. But again, we're interested in the rate of change of this rectangle with respect to x. And so I'm going to write an over dx there as well. And if we wanted to, shorten this, what we've got is f of x times g prime of x plus g of x times f prime of x. And addition's commutative, so if you see it flip-flop the other way, it's completely fine. But yeah, we're multiplying one function times the derivative of the other, and then the other function times the derivative of the first one. If you want to make it really short, you can just say f g prime plus g f prime, and leave all of those of x's out, just because we would understand that x is the variable that we're working with. And so, they show it down here in terms of a limit, which is really cool. They're using u's and v's instead of f's and g's. It's fine. But yeah, they reach the same thing in the end with that, notation. But it's coming from another rectangle like this. Anyways, go ahead and watch that video, see how far you can get. If you get through the whole thing, great. But if you don't, that's fine too. Um, I hope you have a good weekend, and we'll see you on Monday to pick this up. We'll talk about the quotient rule as well, and then um, we'll talk about the derivatives of trigonometric functions and e to the x and stuff like that. So have a good weekend. I mean, actually, go watch that other video and then have a good weekend. All right, we'll see ya. All right. Stop the share and then stop recording.